Welcome to InSPIRESS. I'm PJ, this is Matt.
Hey.
And right now we are standing in the lab, in IPT lab, where the seniors in Mechanical and Aerospace Engineering and Industrial and System Engineering design the spacecraft that you guys are going to be hitching a ride on this semester. So we want to show you a little bit around the lab and show you where these guys actually sit and work on this stuff. So come with me and we'll talk about that over there. So this is one of the rooms where the seniors get together every Tuesday and Thursday. And so you can see in here, this is where they all sit. We have 6 of these rooms this semester where the guys will be. And remember, they're in a senior in Mechanical and Aerospace Engineering or Industrial and System Engineering. And so their job is they design this spacecraft, and this semester we're going to Enceladus, which is one of the moons of Saturn. And Matt will tell you more about Enceladus and all the cool features of it in a little bit. But this is where these guys sit, so if you ever get a chance to come by and see them, this is where they'll be, and they'll be working on their spacecraft. Your job is you're going to design a payload that is then put on the side of the spacecraft or somewhere on it that will go on the way to Enceladus with us. So you're kind of a hitchhiker. You're going to come along the way, and then we're going to make sure and get you off when we get close to the place. So with that, what we'll do now is we'll talk more about the introduction and what the project's all about. And so we'll talk about that in just a few seconds. Okay, so since we showed you where the guys sit this semester, now we need to tell you about the project itself. You can follow along because we doubt you'll really be able to see this really well on the screen behind us. But Matt will make sure and have this posted online on the InSPIRESS website, www.inspires.org, under downloads.
On the downloads page, yeah.
On the downloads page.
It's called Project Introduction.
So that's where all this will, this presentation will be. So we encourage you to download it and be able to follow along with us because we need to make sure you understand all this stuff. So this is the introduction. So we said welcome to InSPIRESS, and we say InSPIRESS like it's no big deal. But really what it stands for, it's an acronym, which is what NASA is all about and the federal government's all about. And so the acronym stands for the Innovative System Project for the Increased Recruitment of Emerging STEM Students, right? See, I even forget it sometimes. So we call it InSPIRESS for short, okay? You will become just like us and be able to create acronyms like crazy, and you'll be spouting them out to people at the open house and everything else that we go through this semester with you. So, what is InSPIRESS? What are we going to ask you to do this semester? So the challenge, like we said before, our seniors are asked by us to design a spacecraft to go to Enceladus. Enceladus is a little teeny tiny moon around Saturn. It's actually pretty neat and cool, literally. And Matt will tell you a lot more about that in a little bit. But so our guys, what?
It's very cool.
Yeah.
Quite cool.
Our guys are going to go there, and so they're designing a spacecraft, not them literally. Their spacecraft will go there and perform some cool science. You know, we're engineers, so the science is kind of the head, but the science stuff that we'll get into in a little bit. So they're going to go there and do that. So what we want you to do in this simulated environment is what we want you to do is then create a payload that can then be accommodated on our spacecraft, okay? So you're the hitchhiker. You're the one that's saying, hey, can I hitch a ride on the way there? And so you'll find out in a little bit, it takes a while to get there, and we have to go by several planets. And so you could decide to jump off along the way. So what we're going to do is ask you to do that for us. So this semester, you're creating this autonomous scientific payload. What do we mean by autonomy? Well, we're going to tell you that once we get there, at least part of your science must be conducted away from us, okay? This is like when you graduate from high school and mom and daddy go, oh, that was so beautiful, and now get out, okay? So your job will be to leave the spacecraft, or mama, and then go off and do your own science, all right?
Not
part of you can stay with you.
Yes.
Part of us, be quiet. Part of you can stay with us. But some of you, some part of your science must be conducted away from us, okay? And that's a big key to this project. You must do that as a part of it, all right? So what does that mean when we tell you to do a payload? Well, what you're going to figure out is you got to figure out the purpose of this science payload, okay? We're not going to prescribe what science you do. Matt will come and tell you and give you a video, right?
Yeah.
A video about all these cool little science things you can do. You could pick one that Matt decides to tell you about, or you could go, he's an idiot, I want to do my own thing, and so you can do it. But you first have to figure that out. And we really want you to sit down and go, what cool stuff could be done? You know, what is some really neat crap out there that would be neat at Enceladus or Venus or Saturn or wherever we go? You know, what kind of neat thing could we do? And why is it important? That's the big key too.
Big deal.
We just can't go, oh, let's go do some crap for fun. Can't do that anymore.
Nope, not anymore.
We got to make sure that we have something in mind when we want to go do this and why it's important to do it. So that's the first thing you're going to do. Second thing you're going to do is understand the engineering design process. He and I teach engineering design to 45 seniors in engineering right now.
As scary as that sounds.
Yes. So we're going to help you along that process to get you involved with it. But it turns out engineering is really just one component of it, because some of you are probably sitting there going, I have no freaking clue what an engineer does, and I have no desire to be an engineer. That's okay. Engineering is part of it, but there's also other parts, like marketing the idea. If you have a great idea, but you can't tell anybody about it, who cares,
That's
right? So you got to be able to market it, and you've got to be able to communicate it to the world. And so those are components of this as well. So it's not only about the engineering, there's other parts of this as well, okay? And last but not least, you're going to learn about soft skills, is what we call them in engineering, okay? So, teamwork. You're going to be put on teams. If your teacher hasn't already put you in teams, you're going to be on teams. So you're going to have to learn how to work together. You might want to kill each other by the end of this, but you're going to do it.
Probably
okay?
so. That's okay. That's natural.
So teaming is a part of this. Each of you should have a different personality. Well, maybe not. But we hope there's different personalities on the team. Like, he is very different from me. Believe me. He's crazy. I'm smart.
I'm better.
Yeah, whatever. So that's a big part of this, is that you need personalities. You need different strengths and weaknesses on the team. Okay? So that's a part of that. Presentation. You're going to have to learn how to present to people in life. If you don't like it, tough luck. Get over it. You're going to have to do it a lot in life. And so you're going to present to people. You're going to present to college professors first off, and then eventually you'll culminate in presenting to people from the local aerospace community here in Huntsville. NASA people, Army people, DOD, you know, all over, Boeing, all of them are going to come in and see you. And so you're going to learn how to do that. And so you can survive it. It's only 15 minutes and you can and get through it, okay? And last you're going to do is reporting, okay? I hate to tell everybody, and I hate it more than anybody, but English is important, okay? And so writing is important. And so engineers are like, we don't like to hear about that. But you're going to have to report out stuff, okay? You're going to have some documents that are due. And so that's all a part of this when we do this together. So developing the payload is a part of it, but there's this bigger thing that's out there that you're going to be doing this semester.
Like he said, you can have the best payload in the world, but if you can't explain it to someone, it doesn't matter. So it's communication, whether it's presenting in front of somebody or whether it's the written word on a piece of paper, it's very important.
And see, Matt must use his hands to
yes,
talk to
if you tied my hands, I could not speak anymore.
Yes. Okay, so what are we going to give you? Okay, we've told you you got to create this wonderful science payload. You got to hitch a ride with us. But what are we going to give you to be able to do that? Right? You got to have resources. So what we've decided to do is we will give you five kilograms, not 5, not 10, 5 kilograms of mass. Okay. That doesn't seem like a lot, but to a spacecraft, that's a huge deal. That is a lot of mass to give a spacecraft.
It's about 11 pounds on Earth.
Yeah. So we're going to give you 5 kilograms of mass that you can use. All right. Next, we're going to also give you is a volume. Okay. The volume is, if we found a box. Oh, Matt's going to go find a box. So the volume, when you are stowed on our spacecraft, can be no bigger than this box. It's supposed to be the size of a 10-ream box of paper. And you've got those all over your high school, so you can go get one and make sure you fit in it. So when you are stowed, when you're all nice and cozy and tight inside there, that's what you got to fit.
When you're on board the spacecraft, you got to fit inside this box.
The second you leave, you can be as big as you want to be, right? Gigantic football field size for all I care. But when you're stowed, you got to sit inside this. Okay? So that's the second thing you got to do. Yes. Third thing, you have to survive the environment that we're going to. Okay? While you're all nice and tucked inside our spacecraft in that nice stowed position, right? You will be guaranteed that we will keep you alive. All right? So the UAH spacecraft will say, "Oh, little child, we'll keep you all fed and happy, and it'll be fun. And we'll keep you nice and warm, and it'll be a nice little ride, okay? The second we say get out, you're on your own, whether that's in a really hot place or a really cold place. And believe me, the places we're going aren't nice like, woo, Earth. No. It's not that way at all. So you've got to be able to survive that environment. And also you must figure out what that environment is, okay? We're not going to tell you. When you go, I'm going to go to Enceladus and you blah, 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 then you better tell us, well, on Enceladus, it's cold and it's blah, blah, blah cold, you know, and give me some numbers, stuff like that. You have to do that as a part of this. And last but not least, you can't harm our spacecraft, okay? You cannot go terrorist on us. Nope. That is not allowed. No, bad idea. So you must be careful. You can't shoot stuff and make it come back to the spacecraft.
It's just rude.
That's a really bad idea. You know, taking out our spacecraft.
It's not cool.
Yeah. So make sure you cannot do any harm to us. There can be no explosions on your payload. No.
Every year.
Every year we get somebody who wants to sneak that in and try to do a boom. So you cannot do that.
That includes pressurized containers. Those things explode too.
Yes. All that is off.
We'll talk more about this as the semester goes, because you'll come up with some crazy ideas, I guarantee you.
Yep.
But
definitely.
We'll be there to go. 9.
Yes. So you can see, I think on the next chart, no, maybe not. Let's go back. So you can see on the right side of this, some of the spacecraft payloads that have been designed before, because you're still probably figuring out what in the world is he talking about. So you can see some of the payloads that have been done before. Now these were all drawn in a CAD program, computer aided design program called Solid Word. Edge, Solid Edge, ST4?
Yes.
4, which you will be getting a copy of if you want it from Matt.
Yes, ST4 or ST5.
Yeah, so you can have one of these cool programs for free to be able to draw stuff like this, or you can just sketch it out by hand. It doesn't matter with us, okay? But you can see some of these payloads. I mean, they've had some projectiles shoot out away from the spacecraft. They've had projectiles fly through the atmosphere. We had a little rover before. That's what this little car thing is. And so all those are kind of neat little things that you do, okay? So that's what we're after.
If you want some compressed gas to shoot your projectiles out, the spacecraft has that on board that you can access. We'll talk more about that as the semester goes on. So there's other resources we can do. You gotta ask for it. You gotta ask about it. So, but we'll talk more about that as the semester goes on. Right now, you're just kind of drinking from a fire hose, so we don't want to hit you with too much. So, but just bear that in mind. There's other resources you can have if you need them to propel yourself away from the spacecraft.
Okay. So, we've told you all about this stuff, about the challenge, about what all we're doing, all that kind of stuff. But let's back up a step and tell you a little bit about how all this begins at NASA, right? So,
in the beginning,
there
was a document.
There's a document. It's how everything starts in the government. NASA has what's called the Planetary Science Division within the Science Mission Directorate. And their job is to explore the solar system. They're forbidden from touching Earth or the Moon or the Sun. Beyond that, they can do whatever they want to do. They've even got the Moon back lately, haven't they?
Yeah, like the rover that just landed on Mars not too long ago. The big one, that was part of the same, Curiosity, thank you. That was part of the same Planetary Science Division that explores everywhere. They sent a probe to Jupiter recently called Juno. Yeah. So they explore the entire solar system, always unmanned.
Right.
That means no humans on board.
No hamsters, no rats,
or monkeys.
Monkeys, no,
dogs,
you can't do that anywhere.
Anything that breathes, basically, is not on board.
No, it's a bad idea.
Yes, it's just rude.
And it's just messy.
Yeah.
You know? Yeah.
Smells bad.
Back on track here.
Okay.
What the Planetary Science Division does every 10 years in what's called the decadal survey is they say,
10 years.
Scientists, tell us what we should do in the next 10 years. Okay? Hence the word decadal survey. So they come up with this document, they fight a while, and they talk about it, and these scientists you can see here, they all come together and say, okay, we think you should go do blah, 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 right? So one of the theoretical missions that they're interested in is something to Enceladus. And so what we're after is, okay, well, what could that look like, okay? So once you get all that under control and they decide on this, this mission, they then get the scientists back together and say, so what should we do? How should we do it? what should we look for, because we don't have a ton of money, we only have a little bit of money. So what should we do, and how should it work? And so these scientists get together, and there are a lot of Sheldons. If you watch Big Bang Theory, there's a lot of them out there. And so they all get together and they figure it out and they fight amongst themselves, but it's fight like, in the science world. They come up with the idea, and so then they sit down with spacecraft people. And so it's like a JPL, the Jet Propulsion Laboratory in California, in Pasadena, California, really big on this stuff. And so they design spacecraft. And so they create the spacecraft, which is kind of what you see down here on the left,
yes.
Bottom left. These are actually two of the spacecraft that the UAH students from previous years have designed. As you can see, there's a lander and there's an orbiter up there. And so they create these spacecraft, they design them up, and this is years of designing and working on this stuff. And then they finally build it. And so you can see in the middle picture here, this is the Cassini spacecraft. It is the largest spacecraft we've ever sent. We sent it to Saturn. It's still out there right now. But you can see right beside it, Matt's going to point, that is a human being, a man standing beside it.
6 foot tall human man right there.
So you can see how big this spacecraft is.
Look on the charts online. Look for this little guy. He's in a white bunny suit.
Yep.
That gives you a scale for how large that spacecraft is.
It is the largest spacecraft we ever sent up. It weighs 6,000 kilograms at liftoff. So what, 12,000 pounds?
Yeah, roughly. A little bit more than that.
Yeah. So after it's built, they then ship it to the Kennedy Space Center in Florida usually, and we launch them on gigantic rockets. We call them launch vehicles, which are actually built here in Decatur, Alabama, which is kind of neat behind that.
Very cool.
But they launch from there and then they go on their way. And what Matt's going to show you in a little bit is how long it takes to get to these places. I mean, these places are so far away from us, we can't really even imagine it. I mean, for me, driving across this country is like, holy moly, and flying to Europe is like, wow. This is years and years and years of traveling, which would just, I couldn't handle it. See, that's why we have robots. Do it for us. Okay, so here's some of the other designs that we've had before, just to show you a preview of what you've got. So you've got some cool drawings. If you look, what's really neat, one of these drawings down here, this one is drawn totally in PowerPoint. They did not use CAD software at all. And so you can see there were robotic arms. We've had projectiles. What?
That top
part was in PowerPoint, yeah. So we've had projectiles shooting out of things. And what's really cool is most of the time what people end up doing is looking at what works really well on Earth and then apply it to something in space, right? So the chief engineer of this team up here, he has asthma, like me. And so this is modeled after an inhaler, which is really cool. This one down here is like a gumball machine, okay? So once you start figuring out what your design is, once you figure out your science objective, you figured out all this wonderful stuff that he's going to work with you on, then you'll get to this point and go, well, what works really well on Earth? Then put it up in space and see if it'll work. And so that's the kind of thing that we do with this class.
The objective, I mean, the general idea is take what you know. They knew these things. He knew how an inhaler worked, that it took something that went this way and pushed it that way. The gumball machine, they knew that it was able to push spheres out of it. And that's what they were looking for. They were looking for things that worked on Earth and they applied it to their payload to work in space. It's not rocket science.
So while it's not rocket science, we still need to make sure you understand what a payload is. So last summer, we got the opportunity to go up to the Air and Space Museum in Washington, D.C. And so we're going to show you in a video now a little bit about what a payload is. And you actually get to see what a payload looks like on a mock-up of a spacecraft. So
it's actually the Viking Mars lander that we're going to show you.
Yep.
Hey gang, we are here at the Air and Space Museum in Washington, D.C. This is the Viking lander that landed on Mars in 1976. As you guys can see, it's about the size of a small car. PJ is going to tell you about some of the payloads that are on the Viking lander.
So the cool thing about the Viking lander, when it landed on Mars, it was to look for life. And so what they did is they decided to put an arm on board to scoop up some of the dirt. So you can see the arm right here, and so you can see it's considered a payload, which is what you guys are going to be doing this semester for us. So you can see kind of the size and shape of it, and also on top you can see several of the different experiments that they use on the lander. So you can see kind of the scope, the size of them, and kind of their mass, and so that's what you'll be doing for us this entire semester.
Wasn't that an awesome video from the Air and Space Museum? Now, one thing to notice about the payloads on the Viking Mars lander is that each of them had a specific purpose. They were designed to do a specific thing. They were designed with the science that they were going to perform in mind. It's very, you can't design a payload until you know what science you're going to do. And also, we realize that at this point, you still probably don't know what a payload is. You're going, oh, I don't know what you're talking about. That's okay. You're supposed to be confused right now. If you're confused, then you're in the perfect spot. If you know what you're doing, then you might not really know what you're doing. Okay, so, but the important thing about a payload is that it's designed to accomplish a specific science objective. And so what we're going to talk to you now is we're going to go briefly over some of the science objectives that our students who are designing the large spacecraft, these are their science objectives. These are the science objectives that they have to accomplish. Your science can complement this science, complement with an E, not like, you know, oh, that's beautiful science, but you can do science that is complementary to their science, or you can do some similar science, some science that would confirm their science. Now, and everything I'm going to show you also, it is specific to Enceladus, and we'll talk more about other planetary bodies that you can visit as well. But so, Enceladus is a unique planet, or a unique moon rather. It's basically a big ball of ice. And, well, it's a small ball of ice, but in terms of balls of ice, like, it's rather large because it's the size of a moon. So anyway, it's like 300 miles across. And so, the most interesting thing about Enceladus are these things. There's these things that the scientists call tiger stripes. And if you'll ignore the name of them, it's actually pretty cool. They're these crevasses, which basically are big scratches in the planet that were formed by plate tectonics. You know, this big. It's kind of like
trying to sound smart for you.
Yeah, I know. I'm trying to sound smart, but it's like a big Grand Canyon type thing. And out of these scratches at the south pole of Enceladus, these plumes shoot. There's 4 of them, yeah. These plumes shoot out, and these plumes are like water ice, basically. There's some salt in there and stuff like that too, but it's mainly water ice. And that's the most interesting thing about Enceladus. And also in this water ice, there's some biological components. They've got carbons and nitrogens and even some ammonias and stuff like that. So the most interesting thing, and the thing that scientists want to do all over our solar system actually, is they want to find life on other planets. And Enceladus actually represents one of the, it's probably one of the planets that if we ever find life on another planet, it's going to be that one. Because
what's really wild is because it's so cold.
Yes.
Yet there's liquid coming out of it.
Yes, it's very cold. It's about minus 173 degrees Celsius, which is extremely cold. It's 173 degrees below, you know, 0, below freezing. But
way colder than an Alabama morning.
Yeah, it's very, very chilly. You have to scrape off your car for a long time on Enceladus.
Yeah.
So
you can start your car.
The number one objective. Yeah, you can start it. So you have there's no air. So the number one objective on Enceladus is, and the number one objective for science in the solar system is to find life. And by life, we don't mean like, oh, hey, how are you? You know, they mean like tiny amoeba or even viruses or just bacteria, stuff like that. Very, very simple cell type organisms.
Not transformers. They're on Mars.
No, they're on Mars. They're on the far side of the moon. Yeah. Don't let that fool you. Yeah. So the biological potential, that's the main objective on Enceladus. That's what most of our college teams are going to be looking for at these tiger stripes on the South Pole. Composition of Enceladus. Because of these tiger stripes, at the South Pole, the chemical makeup of the surface is a lot different than the North Pole, for example. It's extremely different, and the scientists want to study more about the composition of the different parts of the planet. The age of the South Pole, the surface on the South Pole is like 1,000 years old, and you know, people were around Earth at that point. But the age of the surface on the North Pole.
Dr. Farrington?
Yes, Dr. Farrington. Yes, the reason they know it's 1,000 years old is because Dr. Farrington recognized it. So, and the age of the things at the North Pole were billions of years old. Also, Dr. Farrington recognized those. We'll introduce Dr. Farrington to you later.
He's a old guy.
He's extremely, So, cryovolcanism, that's what it is. That's what these tiger stripes are. They're cryovolcanoes. They're volcanoes that spew out cryogenic material. Cryogenic material means frozen stuff, basically. So these volcanoes spew out frozen stuff, ice water. There's salt, and like I said before, there's some biological.
Which is weird, because on Earth, volcanoes don't throw out frozen stuff,
No,
right?
typically that's hot stuff.
Yeah,
so
really hot stuff.
What's going on inside the planet to make these cryovolcanoes work? That's one of the questions that scientists want to know. Why do they work? There's got to be some heat source in there somewhere, something that adds energy to this to make it spew out like that. And the really cool thing actually is that these tiger stripes, Saturn has rings. Everyone knows this, right? When you think of Saturn, you think of the rings around the planet. The outermost ring is called the E ring. They have them A, B, C, D. So, and that's where Enceladus is. Enceladus is in the main part of the E ring. And the ejecta, the stuff that flies out of these plumes on Enceladus, actually make up the outermost ring of Saturn, the E ring, which is really kind of cool, I think. Some of the stuff falls back to Enceladus, like we said, but some of it achieves what's called escape velocity and leaves Enceladus and then forms the E ring of Saturn. Kind of cool.
If it stopped, the E ring would no longer exist.
Yes, exactly. The E ring would just kind of dissipate out. So. Tectonics, like we have on Earth, plate tectonics, we have, movement, basically it's planetary movements and shifts and stuff. They have that on Enceladus also. Scientists want to look at that.
Which causes the earthquake like in Alaska this morning.
Yes, there was an earthquake in Alaska this morning?
You got it.
Oh, you're just going to tell them when we did the video. So,
It
anyway.
doesn't stay up on current events either. So
Yes, I have no idea what's going on. Wasn't there an election?
Yeah.
So, anyway, so tectonics, basically there's movement inside the planet, stuff like that. Scientists want to study that. Tidal heating, scientists want to study that as well. That's where a planet is squeezed and pulled and squeezed and pulls, and just like when you move a paperclip a lot, it heats up. The squeezing and pulling on the planet heats it up as well.
And it's squeezed and pulled by gravity.
Yeah, so we'll talk more about this in the science objective, presentation or video rather. So I'm doing a really bad job of just hitting the highlights. And then there's internal structure. That's what the planet is made up of on the inside. We'll tell you more about that later. But they want to know, what does the inside of Enceladus look like? Is it an ocean? Is it rock? What does it look like in there? The Saturn system interaction, like we said before, Enceladus makes up the E ring of Saturn, or this plume that Enceladus kicks out into space makes up the E ring. They want to know more about that. They want to know about the magnetic field interactions. They want to know about the gravity that Enceladus feels as Saturn pulls it and stuff like that. Surface processes, again, that's talking about how the surface of Enceladus, like I said before, it's very, very old at some parts and very, very young at other parts. They want to know how the surface is replenished, and other plate tectonics, and there's other surface processes include things like meteors that hit the surface of the planet. And then these fissures that form in different areas, these cracks basically that form in the crust. They want to know when these things occurred, how they occurred, stuff like that. That's what scientists look at. And again, these are the science objectives for our college students, not for you guys necessarily. This only deals with Enceladus. You guys will have more opportunities that we'll talk about in just a minute. But before we go on, we wanted to show you a video of Carolyn Porco, correct?
Sure.
She's a world-renowned scientist, expert on Enceladus, and she's going to tell you.
Good buddy of Matt's.
Yeah, real good friend of mine. Yeah. She's going to tell you more about Enceladus, and you're going to say, well, there's a dramatic, actually quite dramatic video we'll show you right now.
After nearly 8 months collecting data of Saturn and its rings, Cassini makes its way to one of the closer moons. This tiny ball of ice, only 300 miles across, is Enceladus. These Cassini images reveal a glistening white surface, unlike any other of Saturn's moons. It is carved with crevasses, ridges, and cracks. And stretching out across the South Pole, Cassini photographs these strange large cracks seen here in blue. 4 parallel fissures scientists named the Tiger Stripes. They are 75 miles long and hundreds of feet deep. They look a lot like fault lines on Earth.
Enceladus was a major focus for the Cassini mission. It was clear that there had been something going on Enceladus in the past. The question was there anything going on Enceladus at present?
On another flyby, Cassini's thermal imaging sensors reveal something unexpected. At the South Pole, the tiger stripes should be colder than the rest of the moon, but they are radiating heat. Though still a frigid minus 120 degrees, the cracks are more than 200 degrees warmer than most of the moon. Then, as Cassini changes its orientation, it sees Enceladus, silhouetted by the sun. And vast jets of ice erupting into space. These actual images reveal the jets are blasting hundreds of miles out from the tiger stripes. Carolyn and her team are stunned.
Never did we expect that we were going to see something like a whole forest of jets shooting hundreds of kilometers into the sky above Enceladus. It was like nothing we'd ever seen before.
Could Enceladus have an internal energy source? Scientists believe that when Enceladus orbits the massive Saturn, friction from gravitational forces causes it to heat up. Melting ice in the moon's interior. They believe the jets consist of liquid water, vaporizing and freezing as it meets the cold vacuum of space. They shoot upwards at 1,200 miles per hour.
Enceladus is being flexed as it's orbiting Saturn. That's like flexing a paperclip. It creates heat inside, and we think the heat maintains the liquid under the surface.
Excited by this discovery, the team programs Cassini to fly through the jets and collect particles. After several fly-throughs, Cassini's spectrometers detect in the jets some of the basic chemical building blocks of life.
That was tremendously exciting to find, because not only do we think there's liquid water there, not only is there an enormous amount of excess heat, but we also have organic materials. And that's the trifecta that we are looking for, the three main ingredients for a habitable zone.
But could this strange and alien world actually support life?
If we are correct that the jets of Enceladus derive from pockets of liquid water in which life might have gotten started, a scoop full of Enceladan snow just might contain the remains of microscopic living organisms.
Hey, wasn't that video riveting? I know, the narrator's awesome. Okay, again, we've only talked about Enceladus so far. That's going to be where our main portion of the college students, that's where their science has to be. They're going to do science around Enceladus. Enceladus is the top right there, and when you're looking on your own that you downloaded, it's going to be on the top right of the chart. So we're going to be at a 200-kilometer orbit around Enceladus, and we're going to land on the surface of Enceladus. So if you want to do science,
You too could.
yeah, you too could do science from orbit around Enceladus, or once the lander lands, you could pop off the lander, stuff like that. Remember, part of your science has to be autonomous. So you need to, we're going to kick you out at some point, just like you're not paying rent or something, you're gone. So, but you don't have to have your entire payload leave the orbiter or the lander. Now, to get to Enceladus, like PJ said before, it takes a long time. It takes about 19 years. Crazy long. I mean, like, most of y'all aren't even 19 years old yet. I don't think any of you are, probably. It makes me feel sad. Anyway, so how did we get there? how do we get to Enceladus? Basically, we do a bunch of maneuvers, flyby maneuvers. Like if you've seen Apollo 13 with Tom Hanks and where they fly on the far side of the moon and come back to gain velocity, to gain speed, so they can get back to Earth. Armageddon, they do that in Armageddon too. With Bruce Willis, yes, yeah. And the Russians. So we do some flybys in order to, first to gain speed to get out to Saturn, and then to slow us down, we do flybys in the opposite direction. You can do a flyby to speed yourself up or a flyby to slow yourself down, depends on how you do it. So first we fly by Venus. The closest we get to Venus is about 1545 kilometers. It's kind of far away. Then we fly by, and then we do 2 Venus flybys actually. Then we kick ourselves out and go toward the Saturn system. And first we fly by Rhea, which is one of the moons of Saturn. It's further out than Enceladus. And we do 30 flybys at 200 kilometers.
How many?
13, not 13, 30, which is my age actually. We do
dog years.
Yeah, we do 30 flybys at 200 kilometers. We'll talk more about what that means to y'all later, but basically we're going to fly by Rhea. Then we'll do 13 flybys of
how many?
Dione. 13, like the unlucky number. Flybys of Dione. And for each one of the flybys of Rhea and Dione, Dione's another moon of Jupiter. It's a little bit closer in than Rhea, but not as close in as Enceladus. And for each of the flybys, there's a corresponding flyby of Saturn. So we do 43 total flybys. Actually do a couple more flybys of Saturn. But those are really far away, 82,000 kilometers. For Rhea and Dione, we're about 200 kilometers from the surface of the planet. And then we finally achieve orbit around Enceladus, and it's a circular orbit at 200 kilometers. And so, if you want to do science, you can do your science doesn't have to be at Enceladus. Your science can be at Venus. You can be at Rhea. You can be at Dione. You can be at Saturn. There's some very interesting stuff. Huh? Or Enceladus, or in the middle somewhere.
Or not that little green, that blue and green one down there.
No, not Earth.
No, can't do that.
No,
because we're crap back at us.
Yeah, we know a lot about Earth. We got Earth covered.
Yeah.
So don't need you to do Earth. You can do something in between. There's been plenty of missions where someone did some, where scientists looked at interstellar dust and stuff. I don't know how you'd have that work, but we'll talk more about that if you want to do something like that.
So Matt, why do we do all this again?
Good question, PJ. Again, the flyby of Venus is to speed us up so that we gain enough speed. It takes a lot of energy to get out to Saturn. So we have to fly by Venus twice, and that gives us enough energy to fly. This is not to scale, by the way, this whole drawing. It gives us enough energy to fly out past Mars, past Jupiter, to get to Saturn. And then once we get to Saturn, we got a lot of energy we need to get rid of. We don't want to just fly right past it or fly and smack into it. That's just bad. So we have to do flybys of Rhea and Dione and Saturn to slow ourselves down so that we can slow down enough to achieve orbit around Enceladus. So that's what all the flybys are for. But you can take advantage of these flybys and perform science at these planets. We've done several missions where we went to outer planets and we flew by Venus, and there's always a team that does the science objective at Venus, and it works out really well. So, not to say you have to do Venus, but that's just an example. You don't have to do Enceladus. You can do Venus, Dione, Rhea, Saturn. And again, there's going to be a video. There's going to be a video called Science Objectives, where we'll go into more detail about some ideas for science that you could perform at these different planets. All right, so once you've decided on your science, once you've figured out what you want to do, your science objective, what your mission is going to be about, then you have your engineering job. There's several jobs. Again, PJ talked about this at the beginning. There's engineering, marketing, and communications. For the engineering portion of the job, this is just what we're talking about right now. The engineering portion of the job, first you have to select your science objective, and we're going to help you with that. We've got another video that'll help you do that. You want to develop a logical flow. Excuse me. You want to start with your science objective, and then flow it down. Say, okay, in order to accomplish this objective, we need to have these instruments. And these instruments require these resources, or they create this much data, or they're this heavy. So you want to have a logical flow from your science objective all the way down to the instruments that you're going to use, and their masses, their powers that they require, and how much data they create, stuff like that. So there's a logical flow that says, okay, in order to accomplish this objective, we got to have this instrument, and this instrument requires these resources. That's what you need to do. That's called the science traceability matrix. We'll help you with that. It's going to be in your book, and it's going to be online. We'll help you with that as well. You want to understand the engineering requirements that are imposed on your payload. We've got different requirements. We have project requirements. We talked about that earlier. You have the size of a box of paper. You got 5 kilograms of mass. Do no harm. Don't go rogue or terrorist on us. That's a no-no. That's just rude too. There's environmental requirements. That's, you know, if you're going to Venus, it's really, really hot. It's very warm. Venus is the hottest planet, actually, not Mercury. A little trivia there. If you're going to Enceladus, it's minus 173 degrees Celsius, extremely cold. Ray and Dione are also cold. Saturn is cold until you get deeper in the atmosphere, then it's hot because it's a lot of pressure. So you want to know where you're going. The environment depends on where you're going. So you want to decide where you're going first, and then figure out what does it look like at this place. What are the environments? Functions. Every payload is going to have specific functions it has to accomplish. We'll talk more about that during the semester, but you want to list all your functions. Those are called functional requirements. And then you got science requirements, of course. To accomplish the science objective, you have the requirements from the science traceability matrix. You want to develop alternative solutions. There's more than one way to skin a cat, okay? Basically, I don't know if that's kind of...
Why not skin a dog?
Because I'm allergic to cats, and cats are evil.
He's a dog person.
Yes.
Ask him about his dog, when he gets beat up by them.
Yeah, my dog is awesome. I got 2 of them. Anyway, there's more than one way to accomplish your mission. We want you guys to look at least 2 different ways to do it, and then at least 2, just to prove that you can do it in several different ways. And then once you've come up with your 2 different solutions to do it, you choose the best solution. We have best in quotes, because what does best really mean? Best could mean different things to me or to PJ or to you. So
it's always better though.
Yeah. So
must be.
You guys come up with at least 2 alternative solutions, and then you pick the best one. We'll show you how to do that. There's a process to do it, of course, because we're engineers. There's a process for everything. Analyze your solution. You want to look at the physics, basically. You know, if you're going to fall from orbit, yeah, and this is where I love this. I love physics.
He's down on his part.
Physics makes the world go around, literally. So, yeah, once you decide on your solution, how you're going to solve this, and there's certain physics equations you need to use to figure out, okay, how fast is it going to hit the ground? What are the forces it's going to feel? How many G's does it feel? Stuff like that. And we'll talk about that. That's later in the semester again. And then you want to build a prototype. It's not a flight for a prototype or even a full-scale prototype. This could be something simple. A couple of years ago, we had a team. They had a probe, and they used 2 salad bowls. Just 2 salad bowls. One was kind of a different shape, and they put aluminum foil around it. That was their prototype. Anything with aluminum foil looks like it belongs in space.
Crinkled.
Yeah, crinkled. It looked like, I mean, it was just awesome looking. People were like, oh, this is so cool. Yep. It was 2 salad bowls with aluminum foil. One team went to Hobby Lobby one year. They got a wooden sphere, a wooden ball, cut it in half, got some cordless phone parts. You know what a cordless phone is? It's a home phone, and then put it inside there and said, this is our probe. They had spherical probes. And they had names for all the different parts. It was like, oh, this is our transmitter, this is, you know. So it's simple stuff, not high dollar stuff, simple stuff, easy stuff. Styrofoam is very popular with these things, but you want to have a prototype, something that shows, something that helps you explain how your probe works and what it does and what it looks like. And then so you can that helps you to explain it to people. We're going to have an open house and a review. We talked about those. So this prototype is just a tool to help you explain your probe or your experiment to people. As PJ said, you can have the best idea in the world, but if you can't market it, if you can't sell it to anybody, then no one cares about it. Marketing your idea. There's several key components to marketing. Team identity, or team ID is what we call it a lot. You got to have a team name. You got to have a logo and a slogan. You typically want these names and logos and slogans, you want it to wrap together with the science. You want everything to make sense together.
Nice package.
Nice package. Put a bow on top. There's always time for a bow. That was from Arthur Christmas. I quote movies a lot. My kids like Pixar and DreamWorks. Anyway, so team identity. You want to make your team name make sense with what you're doing with your science objective. You want it to all wrap together and make sense. On the top right here, we've got 2 posters that were designed. That's under the exhibit. At the end of the semester, we're going to have an open house. And you're going to create an exhibit, like a display and everything for this open house. And you're going to have a poster. You're going to want to have some handouts. You're going to want to have a layout for your exhibit. You're going to want to have everyone dressed similarly, so everyone looks like they're part of a team at the open house. And this is all part of the marketing. You'd be surprised how much this stuff matters. But so up on the top right here, there's 2 posters from previous semesters. This one team was called Dark Side because it was a moon mission and they were on the far side of the moon, even though there is no dark side of the moon. We'll talk about that later. But their team was named Dark Side. They drew this Darth Vader with kind of a psychedelic type look. It was really, really neat looking. It got a lot of attention at open house. That's the point of the poster, to get a lot of attention.
Positive attention.
Positive attention, yes, yes.
Not negative attention.
Negative is bad,
yeah.
By definition. The Europa one is the same. Met was their team name, and they little squiggly line was their logo because they were looking at seismic activity on Europa. And then most teams do a website so that they can help to explain their ideas. This will work at open house. You can use a Google site, something like that. Real easy, not that difficult to do. But marketing is extremely important. Each week during the semester we'll have objectives. We'll have things that we want the engineers to do, things we want the marketers to do, and things we want the communications to people to do as well. And so we want everyone to be on the same page and this tie together nicely.
So where engineering and marketing is important, there's also the communication aspect. It's the last component of it, right? And so there's written documents. These are the things that only certain people will see. Remember, these students, these college kids that are working on their spacecraft, in the end what you create is what's called the Payload Concept Proposal, the PCP. Okay? It can be 5 pages with a title page, which is the 6th page, but inside there you have to describe what you did over this semester and what your payload looks like. It's the only way they see you, okay? That's the only way they know what you did. So if you've done a really great job, you've got to be able to communicate that effectively through this document so they select you. They're going to be a part of the evaluation team. And so that's the only way they'll see you. So we're going to give you a dry run. There's what's called the payload status document, which will be due at the payload status review, which is about halfway through the semester. We'll get you to write up 4 pages, and then we can see how you're working and making sure everything's okay.
It's about 6 or 7 weeks from now.
Yeah, and then you'll add another page by the end about all the stuff you did with Matt afterwards. So all that's going to come together in that document. The other thing you're going to do is briefings, and you're going to do a lot of those. In the end, the only thing that NASA and the review board, this external review board, will see at the final review is this briefing, okay? So we got to get you ready for it. So you're going to have a briefing at what's called the payload status review.
Briefing is a presentation.
Yeah, presentation like this.
Yes.
So what you're going to do is you're going to brief college professors and probably some of the college students that are working with you on what you've done so far and that kind of thing in the payload status review. Then you'll do it again at the payload concept review to get you ready for the final review. So all of these are going to be practices to get you ready for that final review. Because you could have done a great job over semester, but if you can't communicate that in written form or through a briefing, you're not going to be able to win this competition. And after all, this is a competition. So you want to make sure and do those things correctly. So the marketing, the engineering, and the communication all has to come together in one nice, neat little package. And when you do that, that's how you win.
The teams who win have all 3 that work. We've seen lots of teams that only have 1 or 2 of those components that work, and they don't win. Yeah. They'll have a great engineering, or they'll have great marketing, or they might have great communications. But if the other 2, or even 1, are lacking, then you don't end up winning. You got to do well in all 3.
So this next slide shows you that. Okay, this is what a team looks like from our perspective. There's the teacher at the top. He or she is the chief, okay? They are the CEO. They are in charge of this thing. If they, whatever we say, if they tell you a different date, a different time, whatever it is, they override us, We are not a part of that.
They're the boss. Your primary objective, InSPIRESS is really cool. We love it. It's awesome. Your primary objective is to pass your class.
And to make them happy.
And to make your teacher happy. Your teacher's happy, everybody's happy.
Exactly. We don't want the bad things.
No.
Right? So, teacher, chief, CEO, that's the way it goes.
Above us.
Right. So then there's this project manager. This is the chief of the team, all right? We call them the cheerleader, not like woohoo, rah, 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 pom-poms.
No.
But they're the ones that keep everything running, they keep everything smooth, they keep it going. They're usually the one who briefs at the reviews a lot. So this should be somebody that's more outgoing in nature, someone who wants to talk to people, okay? Because, and this person also has to solve the problem because engineering is going to have some issues, communications is going to have some issues, marketing is going to have some issues. This is where the buck stops, is at the project manager.
They need to have strong organizational skills too.
Yes. Make a schedule. Make sure you got everything up to date.
Make sure everybody's doing what they're supposed to do.
Yep. Make sure everybody's got a job on the team. So then there's 3 divisions, as we would call them. Okay? There's the engineering division, which is headed by the chief engineer. We call this the chief geek. Ta-da! Like this man right here.
Chief geeks.
Yes. So the chief engineer makes sure that the payload is being designed correctly. He or she knows the ins and outs of the payload. They know everything about it. When Matt or I walk in the door and say, how much does it weigh this week? They should be able to go, it weighs 2.45 kilograms. You know, they're the ones that do that kind of stuff. They have a team, you know, several people that are engineers that are working on the design with them. But their main job is that payload, getting that sucker under control. Okay? Then there's a communications team, headed by the communications director. These are the people that write the stuff and make sure the briefing gets done. Now, the engineering team creates the content for the briefing and the paper, but the communications team is the one that makes sure it gets all put together. Okay, so could have a great payload, but if the communications team doesn't go, well, we had another paper due, you know, well, guess what? Then there is no paper and there is no design of this thing anymore. So it's their job to make sure all of that happens. Then there's the marketing team, headed by the marketing coordinator. They're the ones that worry mostly about open house. And that's the big thing for open house. Open house will be Wednesday, April 24th at Spraggins Hall here on the UAH campus. And it's the time we bring all of the Huntsville community to see you. Okay? Your job is to impress people who come by who are the judges. And so when they come up and say, what does this payload do? Tell me about your payload. You got to be ready with your whole spiel, you know, all your nice matching, you know, t-shirts to say I'm cool, you know, whatever, and all this stuff that you have out there, handouts, candy, not glitter.
T-shirts should say I'm cool.
Yeah, not glitter.
Yeah. Let's avoid the glitter this year, guys.
Yes, we don't want that. And so you have this big booth. That's their job, is to make sure all of that gets done. That poster has to be submitted early so we can print it and get it ready for you. All of that is the marketing team's job, okay? But all 3 of these, as you can see, are equally important because if you have only 2 of the 3 components, you won't win this competition. It is really fierce. Every semester gets more and more fierce and the competition gets really unbelievable. And so this semester is no different. You've got to have all 3 components to make this work.
And just because you might be on the communications and marketing team doesn't give you a free pass. You don't get to, I don't care about the science, I don't care about the engineering. Everybody has to know what everyone else is up to.
Yep.
It has to all fit together nicely. And if everyone doesn't know what everyone else is up to, you don't have to do that person's job, but you need to know what's going on. So it's important that the marketing and the comm people also know what's going on the engineering side,
right.
And the engineering people know about marketing and comm, and so on and so forth. So everyone needs to know what's going on in the entire team. And that's the PM's job, is to make sure that all that kind of fits together and works together, and make sure everyone's on the same page.
The grand integrator.
Yep.
Yep. So, competition. This is all about competition.
Yes.
And in high school, it's even more than in college.
You want to win.
Right. We hope that's your whole goal, is you want to win this competition.
Winning.
So, this semester, we have 7 high schools in this competition. There's 27 teams? 27 teams?
Sure.
Something like that. 27, somewhere.
Yes.
Yeah, 27. 27 teams. So they're from all over North Alabama and actually El Paso, Texas.
Yep.
So we even have one out there all the way. So what we've done so far is we begin to put you in divisions. There are 6 divisions this semester, divisions A through F, okay? And so once you're assigned, you're at your high school obviously watching this video, but once you're assigned a number, you know, Muscle Shoals 1, Da Vinci 5, Fairview 3, whatever it is, then you can see where you are in the competition, okay? One thing to note, because several high schools have more than one team competing. I think actually everyone does this.
Yes,
semester.
everyone.
The only competition you're up against is what is in your division, vertical, okay? So if you're in class, if Fairview 1 and Fairview 2 are in the same classroom, they are not competing against one another. They can help one another, okay? It is highly encouraged. If something is wrong on Fairview 2, they just can't figure out what to do. Fairview 1's figured it out, tell them, okay? You're not in competition with them. It would be great. You can have high schools win multiple divisions. We have had it every semester. So
Yes, we have.
this past year, last spring, Cold Springs won several divisions. This past semester in fall,
West Point.
West Point, I was going to say Muscle Shoals. West Point won several divisions. So it can be done. So please help out each other and make sure you get this right, okay?
A rising tide lifts all boats.
Okay, whatever you say there. I don't care.
But again, there's no competition between this way. None at all this way. It's
None.
all up and down this way. So
Okay,
you're
so
not competing
remember
against,
that.
you're not competing against other teams in your class.
Yeah, no matter what. And I don't think any high school was
Even in
actually
school,
competing.
no, yeah.
This semester worked out perfect where nobody was competing against anybody else.
Even at your high school.
So, how do you win, right? We've talked about this competition. You might understand now, although he explained it poorly, what a payload looks like, what a payload was.
You'll get it, don't worry.
Eventually you'll get there, about halfway through the semester.
You got it. I got it.
So we talked about that thing, then we've talked about this competition, but now your question should be, well, how do I win, right? That should be your pondering thing right now. So, there are 3 components to how you win this
It's
competition.
the first time we're not using the number 5.
There's 3. Un, deux, trois, right? We're getting ready to go to France. So
Eins, zwei, drei.
he's a German, whatever.
Use your thumb.
Okay, whatever. All right, so components. There are 3 components to winning. First is the open house exhibit. Okay, we talked about that. That is going to be on Wednesday, April 24th, 1 to 5 p.m. here on the campus at UAH in the Spraggins Hall. So what you have to do is there are going to be people from the local Huntsville community, engineers, scientists, secretaries, analysts, anybody.
Communications experts, HR reps,
right,
everything.
all of them.
Housewives, house moms,
They all come
house
in.
dads,
What?
college students.
Yeah. They all come in
My dogs.
and they judge you. So they have a little board and they have criteria which is laid out in your competition rules of what criteria they're going to use. So they sit down and evaluate you. They stay with you for about 10 minutes and do that. So that is 25% of your composite score.
Yep.
Okay? The second component is the payload concept proposal, the PCP. That is the written document that you will submit before the end of the semester to the college students, the UAH college students, who will then evaluate you. They have criteria, which is also located in your competition rules, of what they will be looking for, and they will be scoring you appropriately, okay? So they do that. We give it to them, and they've got a week to finish it up for us. That is 25% of the composite score. And then 1/2, 50% of the composite score is in the final review presentation at the end, okay?
Biggie.
That is currently scheduled for Thursday, May 2nd in Shelby Center here on the campus of UAH.
It'll be in the afternoon.
It'll be afternoon from 2 to 5 p.m., so you won't have to get out of class that much to come to it. But at that point, you will have 15 minutes to brief NASA and local aerospace and industry people on your payload concept. Then they will get 10 minutes to ask you questions. They also have criteria, which is located in your competition rules, that they will use to score you, okay? So then we take the score. There is actually a winner from each of these things for each division. So there's an open house winner per division. There's a payload concept proposal winner per division. And there's a final review per division. Then we take the scores from each of those components and make a composite score overall. And that is the overall winner per division, okay? So there are 6 overall winners. There are 6 open house winners. There are 6 proposal winners, and there are 6 presentation winners.
1 for each division.
Right? So that's how this all works together. It's cool. Okay, so that's the competition. So what do you need to start working on, right? Because we're not there.
No.
We're actually in France.
And we haven't given you your notebook yet either.
Yeah, because that's a little bit too much for you.
We'll talk about that right now.
Yeah. So what you need to do right now? Well, there is this thing called competition rules that I've been talking about, right?
Yes.
They're going to be posted on the website.
Yes, they will. We're not there yet, but they will.
And the notebook's going to be out there for us.
Yes, it will.
So you can go ahead and look at it because he's going to bring you, we'll come together probably, and bring you a notebook, a real one-inch
Physical
binder
hard
notebook.
copy, like print it out.
So we'll print it out for you, so don't worry about printing it out. But go online at www.inspires.org and go to downloads.
Yep, downloads.
Downloads, that part, and you will see the competition rules that you can start reviewing because it will tell you all the different things, the format requirements, everything we have to do with you. It'll also have the book out there.
Notice I'll do this stuff.
Yes. It'll also have the book out there that you can look at as well. The other cool thing that Matt has done on this website, because Matt created the website.
Please don't make
So if it sucks, it's Matt's problem. If it's great, I did all the work. It was beautiful. But no, really, he created the website, which is a really cool website. There are templates out there. We have the payload status document. We got the payload concept proposal.
Yes.
We got the payload status review, the payload concept review. All of those have templates in Word and PowerPoint for you to use. Please download these things and start looking at them to understand what each of them means. Also, what he's done is he's put out the archives section. It's called archives?
Yes, there's a link called archives, a really big page of archives.
So what you can look at is past winners.
Yes.
Go look at what the past years when they went, wow, we won. Like several West Point teams won last semester. Go look at what they did, okay? That'll probably be a pretty good indicator of, whoa, that's what you gotta do to win this puppy. You know, and you can start looking at that and figuring that out. So all that is stuff that you can do before we come and see you after we get back from Paris, okay?
There's also a page called Projects and Events that talks about the stuff that happened during previous semesters. You can read about that. There's a link on the website that says Photos and Videos, which is probably where this video will be on that page as well. But there's also a link to our photos site. You can go and look at previous open houses that we've had. The best examples would be the last two open houses that we had because they were in Sprague's Hall also. But you can see, okay, what does an open house look like? What does an exhibit look like? What's the magnitude of this? What do we got to get ready for? Yep. It'll give you a really good, it'll give you a good preview. A lot of y'all came and visited open house before because we saw some of y'all there.
Try to get that in Cold Springs.
Yes, but these photos will show you, okay, this is what we got to prepare ourselves for as far as open house is concerned. And there's also some previous NASA or previous final review photos up there as well. So
hopefully you're excited. We're really excited.
I can hardly contain myself.
Yes. So we will see you probably the week after we get back from Paris. So I might still be talking to French a little bit.
Yeah.
But
and I will be asleep.
Yeah. So until then, see you later.
Ciao.